Professor received his PhD degree in electrical engineering from the Polytechnic Institute of Brooklyn, New York. Currently, he is since Jan 2018 emeritus professor of electrical engineering at the University of South California in the Los Angeles. He has published close to 600 technical papers and is author and or co-author of 12 books. He is a life member of IEEE, a distinguished member of IEEE Control System Society and fellow of International Fuzzy System Association. He was president of IEEE Control System Society in 1986, a member of Administrative Committee of IEEE Computational Intelligence Society for 9 years, and chairman of its Fuzzy System Technical Committee and the Computing with Word Task Force of that technical committee. Among his awards are 4 IEEE Transaction Best Paper Award or 1984 IEEE Centennial Medal and IEEE Third Millennium Medal of Fuzzy System Pioneer Award from the IEEE Computational Intelligence Society and the Lofty A. Jardine Pioneer Award from the IEEE System Man and Cybernetics Society. According to Google Scholar, as of now, December 5, 2021, he has more than 59,000 citations and H index of 98 and I-10 index of 310. His presently research interests include type 2 fuzzy logic system, XAI for rule-based system. So welcome you, sir, for short introduction as per your instruction.
Okay, well, thank you very much. For those of you who don't know it, I live in Los Angeles, California, and it's 6 o'clock in the morning here. So I have a cup of coffee next to me to keep me awake. So let me share my screen. I have to admit that I've never used Webex before, so I hope this works. Okay, you're gonna have to guide me through this. I don't use Webex, I use Zoom. And how do I share my screen on Webex?
Now it's working, sir. We can see your screen.
You can what?
Yes, we can see your screen, sir.
I know you can see my screen, but I have to turn my slides on. I want to share my slides.
Make sir co-host.
Yeah, that's right. You have to make me the co-host. Ah, okay, thank you. I'm trying to access my presentation by sharing, and I'm unable to do that.
You have to open your PPT right now.
I have to what?
Because you already shared that screen.
Yeah, I have it on sharing, but I'm not able to access my my desktop. How do I access my desktop?
I think you simply go on the next tab, I think, in the PPT section.
Sir, in sharing
Yes.
option, you can choose directly your PPT whether it's open or not. There is an option that
Well, I clicked on share and it says I'm sharing my screen. So can you see these slides now?
Yes, sir.
Oh, okay. So I'm going to put it on full screen and tell me whether you can see that on full screen. Can you see that?
Yes, sir.
Excellent. Sorry for the delay, people. So in this course, you've learned about type 1 and type 2 fuzzy systems. And one of the questions that's concerned me for a long time is why should we use type 2? Is there a way to anticipate that we can get better performance? And so I spent some time studying this, and I'm going to explain how you can tell people why it's possible to get better performance using type 2 fuzzy systems rather than using type 1 fuzzy systems. Let me ask you again. Everything okay? You can hear me?
Yes.
Yes,
Good.
sir.
Okay. So here's the crucial question. Why does improved performance occur as one goes from a crisp to a type 1 to interval type 2, even to general type 2 fuzzy systems, and from singleton fuzzification to non-singleton fuzzification? This is crucial because many people don't like, they're even prejudiced about fuzzy systems on general principles. Unless we're able to easily answer this question, they'll ignore what we're doing. Well, there's a number of possible answers. They're a bit vague, though. So let me give you some of these answers. You might say, well, a fuzzy system is inherently nonlinear, and so it should perform better than a linear system because most real-world systems are nonlinear. Here's another one. A fuzzy system easily achieves smooth transitions across its input state space because of its overlapping membership functions. It has a variable structure, something that can't be achieved easily at all using a non-fuzzy system. Or fuzzy systems have more design degrees of freedom. You have the membership function parameters and the consequent parameters than do non-fuzzy systems. And in fact, an interval type 2 and a general type 2 fuzzy systems, they have even more design degree of freedoms than does a type 1 or an interval fuzzy systems. Those are high-level, general, vague reasons why you might expect a fuzzy system to outperform a non-fuzzy, a type 2 to outperform a type 1. Frankly, they're a little too vague to me. So here's a fact. A traditional performance analysis begins with a specific application like control. So I had this idea, and the idea was that there ought to be a common component to all performance analyses, after which the rest of the performance analysis is application dependent. So I'm going to describe a new and non-vague answer to that crucial question. And I'm going to show you that it's the greater sculpting of the state space that lets a type 1 fuzzy system outperform a crisp system, an interval type 2 fuzzy system outperform a type 1 fuzzy system, and so on and so forth. Of course, I have to explain what I mean by sculpting of the state space. And that's what's going to take up most of my time today. So to begin, I want to remind you of what a rule-based fuzzy system is. Okay. It contains 4 blocks. The heart of it is a collection of rules, if-then rules. And those are turned into mathematics using fuzzy sets and the mathematics associating with the inferencing of fuzzy rules. You make measurements, and the measurements you make are numbers. They're crisp inputs. And so in order to be compatible with a fuzzy system, you have to first convert those numbers into fuzzy sets, and that's done by the fuzzifier. So the input comes in, it's fuzzified. Those fuzzy input sets activate the engine, and through a mathematical inferencing process, you get fuzzy output sets. We really want numbers, or in some applications, you might want words. And then you go through an output processor and you get that output. Basically, the block that I put around those 4 component blocks can be represented at a high level as a nonlinear function. The output y is a nonlinear function of a vector of inputs. Now, there's different ways that you can model the input. If you believe that there's no uncertainty about your measurements, then you use what's called Singleton Fuzzification, where the measurement, to distinguish it from the input variable, is designated with a prime. X prime is the measured value of X. And if you believe that there's no uncertainty, then we can create a membership function, okay, a singleton fuzzy set, where the membership is 1 when X is equal to X prime, and it's 0 everywhere else. In more advanced fuzzy systems, if there's uncertainty about the measurement, then you model that measurement as a fuzzy number. I'm not going to have time to go into that today, maybe later. So here's the structure of the rule antecedents. There are P inputs, and all of the inputs are connected by the word and. The capital F's are the fuzzy sets. So if X1 is low and X2 is moderate and XP is high, then you get the output. The most important computation in this rule-based system is something that I call the firing level. Okay, and that takes you from the measurements through the antecedents of the rules. And F sub L is the firing level for the Lth rule. The total number of rules I like to use is capital M. And it's a T-norm. The T-norm that we use is usually the minimum or the product of the firing level for each rule. For each rule. That firing level is the product, is the T-norm of the membership functions for each of the P antecedents. Okay, so a measurement comes in, it's converted into a singleton fuzzy set, and then you compute this firing level. So in a type 1 fuzzy system, a firing level contributes to its output only if it's non-zero. That may sound trivial to you, but so that you can flow to the output. So that's what I mean contribute. In a type 1 fuzzy system, it's the membership functions of the rule antecedents that establish exactly where this occurs in the state space. And it occurs when the membership functions of all the antecedents are simultaneously non-zero. So we say when a firing level is computed using either the minimum or product T-norms, its non-zero occurrence over the p-dimensional state space can be established by examining the components of the firing level separately over each universe and then combining those results for all p variables by using either the minimum or the product t norms. And the reason that that's true is because the minimum of all these firing quantities is 0 if any of them is 0. The same for the product. What this means is that when we begin examining this concept of sculpting the state space, we can begin by doing it for each variable separately. And that's real easy to do, as you're going to see. So now I'm going to explain what I mean by a first order rule partition. Just to let you know, they're going to be second order rule partitions, and for interval type 2 fuzzy systems, another kind of partition called a novelty partition. But let's start slowly. I'm going to begin with type 1 fuzzy systems, and then I'm going to go to interval type 2, because one of my goals here is to be able to explain in a way that will let you do this why a type 2 fuzzy system has the potential to outperform a type 1 fuzzy system. So in a type 1 fuzzy system, a type 1 first order rule partition of the state space for that variable is a collection of non-overlapping intervals in x sub I, in each of which the same number of same rules is fired, whose firing levels contribute to the output of that type 1 system. Now, there's a lot of verbiage here, and it may be confusing. So I'm going to go through a construction procedure that's very simple, and then you'll see what I'm talking about. So we're going to see that first order rule partitions provide what I call a coarse sculpting of the state space. So here's an example. I'm going to build up this diagram for you, but I first want you to look at this figure carefully. It's for a single variable x1, and there's only 3 membership functions: a left shoulder, an interior, and a right shoulder that are called low, moderate, and high. And low and moderate overlap, and moderate and high overlap. That's the blue membership functions. And in a trivial rule-based fuzzy system that only has 1 variable, there'd be 3 rules. If x1 is low, then the output is this. If x1 is moderate, then the output is that. If x1 is high. Okay, so there's 3 rules. What I'm going to demonstrate by a construction procedure is that there are 5 first-order rule partitions. And then we'll see what the number of rules are in each of them. And this is a notation that I'll explain. So let me explain how I obtained this diagram. So let's begin with the 3 membership functions. And I demarcate the endpoints of the domain 0 to 10. And now what I do, imagine that I have a virtual dashed line. I'm going to begin at the left, and I'm going to sweep to the right. Everywhere between 0 and A, I only activate 1 rule, 1 membership function. So in this region between 0 and A, the number of rules that fire is 1. Okay, so in this region, 2 rules are activated. Moving ahead to the right, between B and C, only 1 rule is activated. If x1 is M, then. Continuing, between C and D, 2 rules are activated. And finally, between D and 10, 5 rules are activated. Okay, so what we see is that a 3-rule system with these membership functions partitions the 1-dimensional state space into 5 first-order rule partitions, where the number of rules that are active is at most 2. So we have a 3-rule system, but in some regions of the state space, only 1 rule is active, and in some regions, 2 rules are active. So this is a notation where to the left of the vertical bar is the name of the partition. Now I'm just using numbers for the names, 1, 2, 3, 4, 5. Okay, and so in this first order rule partition number 1, 1 rule fires. In partition 2, 2 rules fire, and so on and so forth. So now let's go from 1 variable to 2 variables. And here's a construction for determining the first order rule partitions in my 2-dimensional state space. Okay, what I've done is on each axis, I've superimposed the membership functions for that variable. Okay, and you don't have to have the same number of membership functions for each variable, but I want to keep this real simple. By the way, let me mention something. Let's go back to this last diagram. This is an important observation. These dashed orange lines always occur where the membership function either goes from 0 to a non-zero value or ends from a non-zero value to a 0 value. And so you can look along the x1 axis and insert these partition lines where the membership functions cross 0. That's a simple way to do it. You don't have to go through this sweeping business. And that's why I have these orange circles. That's where they're located. So what I've done then is I've located these orange circles at both sets of membership functions, and then I've drawn vertical lines for x1 and horizontal lines for x2. And what this does is it partitions my 2-dimensional state space into a bunch of rectangles. Now for 2 variables, each described by 3 membership functions, there would be 9 rules. Observe, though, that there are 25 first-order rule partitions, 5 times 5. Now, let me explain how I got the numbers in these partitions, because they're much smaller than 9. So let's go to this one here, 0A, 0A. So what I do is, I see that in this region, only 1 rule fires. If x1 is low and x2 is low. If I go up to here, when x1 is between 0 and A, and x2 is between A and B, I see that x1 only intersects low, but x2 intersects low and medium. So 2 rules fire. How about this region with a 4? Well, now x1 is between A and B, and so L and M are active. And x2 is between A and B, and L and M are also active, so 2 times 2 is 4. So what I want you to observe is that even though this is a 9-rule system, most of the time, only 1 or 2 rules are firing. Sometimes in these 4 regions, 4 rules. 4 is considerably smaller than 9. So here's what happens in chosen the 3 membership functions for Z1, Z2, and Z3 so that there's a region where between B and C, 3 membership functions are active. And so that's how you get 9. 3 times 3 is 9. Or here, 3 times 2 is 6. So in this 25-rule system, in this 9-rule system, there is a region where all 9 rules fire. Most of the times, though, a smaller number of rules fires. So let me explain how you can use this diagram to get a sense of what's going on in a rule-based fuzzy systems. let's start at this point. And the blue trajectory is like a phase plane trajectory. I'm moving through the system, and I'm terminating at some point where all 9 rules fire. And what I want you to observe is as you move along this trajectory, the output of this fuzzy system change, the formula f of x basically changes. It begins where only 2 terms are active. It then moves on, and now 4 terms are active, then 6, 4, 6, 4, 2, 3, 4, 6. This is what I'd like to call an adaptive variable structure fuzzy system. Okay, so I think you can see that the first order rule partitions let you tell people that a fuzzy system is an adaptive variable structure system, and it partitions the state space automatically by virtue of its overlapping membership functions. And most of the time, only a small subset of the rules fire. Now let's move on to an interval type 2 fuzzy system, because again, I want to remind you, my goal here is to be able to explain why a type 2 fuzzy system has the potential to outperform a type 1 fuzzy system. So here is the structure, the canonical structure of an interval type 2 fuzzy system. The only difference really between it and a type 1 is that now everything has to be in terms of interval type 2 fuzzy sets. And if I want to get back to a number, I have to go from the output of the inference engine through something called type reduction, which may give me an interval of numbers, and then through a defuzzifier. Now, what I'd like to tell you is that there are structures for interval type 2 fuzzy systems where you can bypass type reduction. You can go directly to defuzzification. So again, if the input is a singleton, then we model it using the same kind of membership functions. The antecedents of the rules now, instead of the membership function for x1 being modeled as a type 1 fuzzy sets, it's modeled by an interval type 2 fuzzy set. And we use this tilde notation to distinguish a type 2 from a type 1 fuzzy set. And for an interval type 2 fuzzy system, instead of having a firing level, we have a firing interval. And a firing interval is defined or described by 2 numbers, the endpoints, the lower and the upper bounds of that firing interval. And the lower bound is given by the t-norm of the lower bound of the membership functions for the antecedents at this input, xi prime. And the upper bound on the firing level is given by the t-norm of the upper membership functions at xi. Now what I'm going to do is I'm going to parallel everything I said for a type 1 fuzzy system for this interval type 2 fuzzy system. So we say that in an interval type 2 fuzzy system, a firing interval is said to contribute to its output only if it's non-zero. I mean, that makes sense. If this interval is 0 because I'm not activating the membership functions, then it's not going to contribute anything to the output. Interesting. Established exactly where the firing intervals contribute to the output. Why is that? Well, if the upper membership function is 0, then a lower membership function must also be 0, because the lower membership function can never be larger than the upper membership function. Okay. So after you go through and you compute the firing interval, then you have to decide what kind of output processing you want to use. I'm going to focus today on type reduction, center of sets type reduction. And in center of sets type reduction, you combine the upper and lower values, or the left and right ends of the firing intervals, with some number associated with the consequent of each rule. And the trick is to determine when you switch from this first term to the second term. That is, how do you determine this capital L and how do you determine this capital R? Okay. There are algorithms. There's a very large literature on how to do that. My student Nilesh Karnik was the first one to look at this problem, and we have algorithms that are called the KM algorithms. And since that time, there are other algorithms that have been invented. There's no closed form. They're iterative algorithms, but they're very fast. I'm not going to go through those algorithms. I'm more interested in this structure. So let me remind you again. Input comes in, you compute the firing interval. Then you go from the firing interval through type reduction. Type reduction gives you these two numbers, YL, YR. Then you average those two to get the output of your fuzzy system. So just as for a type 1 fuzzy system, when I talked about a type 1 first order rule partition, I now want to talk about an interval type 2 first order rule partition. Basically, the words here are the same as they were for the type 1 first order rule partition. So here's the construction, and I'm not going to go through a buildup of this. I'm just going to walk you through it from left to right. Now what I've done is I've taken those three membership functions, low, moderate, and high, and I've assigned some uncertainty to them. And so that they now become footprints of uncertainty, L with an over tilde. And you can see that for a while it's known perfectly, and then it branches into a triangle, and the shaded region is its footprint of uncertainty. There's all sorts of shapes that you can have for these footprints of uncertainty. I'm using, in this example, triangles. Okay. And you can see that the left end of the footprint of uncertainty for medium or moderate overlaps with the right end of the footprint of uncertainty for low. So let's start at the left. Between 0 and A, I only activate low. Only one rule is going to fire. Between A and B, I activate both low and moderate. Now, it may be a little confusing. Every time I look at this diagram, I say, wait a second, this FOU for low starts, somewhere in that region. That's okay. It just means that there's a region where there's no uncertainty about low, but then when you get to the right of that, you get uncertainty. So what that means in the jargon of interval type 2 is that in this region between A prime and I didn't label it, but it's over here, the upper and lower membership functions for low are the same. Okay. So notice I put the orange circle where we begin with firing 2 rules and we end. And you'll notice that these orange circles occur where the upper membership functions of the interval type 2 fuzzy sets cross the X1 axis. Rule. So there's the construction for the interval type 2 first order rule partition. So let's move on to 2 variables. Okay, so I'm doing the same sort of thing. I'm locating the FOUs for X1 and X2 on their axes. I'm putting these orange circles where the upper membership functions intersect their axis. And then for x1, I'm drawing vertical lines. And for x2, I'm drawing horizontal lines. And now I'm determining, you have to do this for each of these rectangles, how many rules are active. And so, for example, with this 4, between A prime and B prime on x1, and A prime and B prime on x2, L and M are both active, so 2 times 2 is 4. Okay, so we get a diagram that again has 25 interval type 2 first order rule partition, same number as a type 1. Okay, so what's different? Aha, now let's compare these two. Finally, we're able to get to a point where we can make some definitive comparisons and statements. When you compare these two first order rule partition diagrams side by side, what we see is that the regions where one rule is fired when you use interval type 2 fuzzy sets is much smaller than when you use type 1 fuzzy sets. And the region where 4 rules fire are vastly larger. Okay? So what that means is that membership function uncertainty tends to fire more rules more often and fewer rules less often. That's the way uncertainty about membership functions can be explained. If you have uncertainty, you have to hedge your bet. And the way you hedge your bet is you downplay the regions, the size of the region where only one rule. I mean, let's face it, if you fire one rule, you're absolutely certain that that's the thing that contributed. But when uncertainty is present, you may be certain, but you're certain in a much smaller region. And you can see that the regions where you fire 4 rule, again, I'm repeating myself, are much larger. So there's much more region in the state space where you're firing more rules to compensate for the uncertainty. So we can generalize this. In a type 1 or an interval fuzzy system, a type 1 or an interval type 2 first order rule partition of the p-dimensional state space is a collection of non-overlapping hyperrectangles in the state space, in each of which the same number of same rules is fired, whose firing levels or intervals contribute to the output of that fuzzy system. Now, in the journal article, whose reference I'll give you, I developed general formulas for 2 things. You want to know how many regions there are in your state space and how many rules fire in each region. Okay. The star here and the subscript can be replaced either by type 1 or interval type 2. The beauty about these formulas is that they tell you that in order to compute these counts, you first have to go to each variable separately and construct its first order rule partition diagram. That will give you the N1 and the N sub R for each variable. It's as simple as that. Okay, so I've described now a construction that lets you introduce a second order rule partition. A second order rule partition occurs when the membership function of a type 1 fuzzy set that's associated with a variable changes its mathematical formula within a first order rule partition. Second order rule partitions, as we'll see, represent a fine sculpting of the state space. So here's a diagram, and let me explain how I constructed this diagram and what all the terminology means. For each variable, I start with its first order rule partition diagram. Okay, and those first order rule partitions are labeled here. I have the orange dashed lines. And now what I do is I look in each of these first order rule partitions to see if a membership function has changed its mathematical formula. So let's see what happens in this first order rule partition between 0 and A. Well, L is a constant up until, there's a breakpoint, and then it starts to become a downward sloping function. And so now I put a dotted vertical line in there. Let's continue. Between A and B, you can see that the formulas for the membership functions don't change. They stay the same. Now let's go between B and C. Moving from B, I see that M is upward sloping, and then at this breakpoint or kink, it changes its formula. It becomes a horizontal. And then at this kink, it becomes negative. So I put in two brown dashed lines. Between C and D, nothing changes. And between D and 10, yes, there's a change. Okay, so now I've got these brown dotted lines. And now let's go and let me explain what the notation is. Between 0 and this first dashed dotted brown line, I have my first second order rule partition that resides in the first order rule partition. So the first number 1 is the name of the first order rule partition. The second number is now the name of the second order rule partition that lies within the first order rule partition number 1. This vertical arrow now indicates that the name of this partition, second order partition, is 2. There's no second order partitions in first order partition 2. Here, this is the first order partition 3. Here's the second order, the first second order partition, the second and the third, and so on and so forth. And so what I see, if I count the number of second order type 1 rule partitions, is that there are 7 of them. So let me back off again. For this variable, there are 3 rules. The state space is partitioned coarsely into 5 non-overlapping first order rule partitions. There are a total of 7 second order rule partitions. Oh, I'm sorry. I forgot about this. I told you, it's early in the morning for me. I guess I'm showing the buildup of this diagram. What I want you to observe is that the second order rule partitions for a type 1 fuzzy system always occur where the upper membership, where the membership function changes its value. Okay. And so you can see I put brown circles to indicate where that occurs. Okay, so let's move now to 2 variables. And here's the construction. Bear with me, the right diagram looks very complicated, but it's not. Here's the first order rule partition diagram on the left, whose construction a brown circle wherever the membership function changes its mathematical formula. And I do the same thing for the vertical. And then I project upward vertically for x1, wherever those changes occur, using dashed lines, and the same for x2. Okay, And now I have to go to each one of these 25 regions and I have to count. There's no simple way to do this. You have to count. So let's go to this first order rule partition down when x1 is between 0a and x2 is between 0a. And you can see that there are 4 regions. What this means is that even though only one rule fires, depending upon where you are in that region, you have different mathematical formulas. So there's variability within the first order rule partition. Remember? So the number of terms that contribute to the output remains the same, but the formula changes because the membership functions change. So it's adaptive. Let's go to this region in the middle where there are 9 second order rule partitions. Even though only one rule fires, because the membership functions are changing 3 times for x1 and 3 times for x2, there are 9 regions. So what this means is that if you count up all the second order rule partitions, there are 77 of them. That's a lot larger than multiplying the 2 first order partition numbers 7 by 7. So there's a huge amount of variability going on in this simple 2-variable type 1 fuzzy system. Okay, so again, you can explain to people that not only does a rule-based fuzzy system sculpt the state space coarsely, but within each first order partition, it further partitions things more finely. Think of a sculptor starting with a block of granite, Michelangelo, for example, and he works with a tool and he carves and he gets a coarse sculpting. Then he takes a different tool and he starts to chisel away, make things finer and finer. That's what's going in this fuzzy system. In each of these regions, when the membership functions change, you're chiseling away the structure of the nonlinear system. And this is happening automatically due to the overlap of each of the membership functions for x1 and x2. Now let's go to an interval type 2 fuzzy system. Okay, we have its second order rule partitions. Interestingly, we're going to see that they occur not only when the upper membership functions change, I call those kinks, but finally, we're going to bring in the lower membership functions. I want to remind you, the lower membership functions have played no role at all in determining where the first order rule partitions are. But they're going to play a role now in the second order rule partitions. So here's the construction procedure. Again, I'm not going to build this one up. You start with the first order rule partition diagram for each variable. Okay, so the orange dashed lines. So you begin with that. Okay, and now what you do is you could scan, but let me just tell you. What I'm going to do is I'm going to begin by looking where the upper membership functions change their mathematical formula. I get these points. I've used a little brown circle. We've already accounted where the upper membership functions become 0, so we don't have to do that again. That's what's determined the first order rule partition. Now we look at the lower membership functions for the first time. Axis. Now, if I had more complicated FOUs, instead of triangles, I would have additional points where the lower membership functions change their mathematical formula. Okay. So now let's see how I label each of these interval type 2 second order rule partitions. Okay, between 0 and A prime, nothing's changed. Okay, in fact, until I get to this brown circle here where I've inserted, there's only hang on a minute. Oh, I'm sorry. I didn't label the, there are no second order rule partitions between 0 and A prime. Okay, between A prime and B prime, I have my first order rule partition 2, but I can see that there are 1, 2, 3, there are 4 second order rule partitions. So on and so forth. You go through this, and what you find out that there are 9 interval type 2 second order rule partitions. So remember, for the type 1 fuzzy system, there were 7. Now, because there are lower membership functions, there are 9. Let's extend this from a trivial first order system to a 2-variable system. And now you go through the same construction procedure. You begin with the first order rule partition diagram for the 2 variables. You locate all the places where either the upper membership functions change or the lower membership function formulas change. And you project up all the lines, vertical lines for X1, horizontal lines for X2. The diagram looks messy. Now what you got to do is, and again, there's no simple way, you have to go to each of these rectangles and count. Now, some of you may be looking and saying, wow, in this region here, when X1 is between A prime and B prime, and X2 is between C prime and D prime, there are 20 second order rule partitions. Here's one over here with his 25. Do a count, and you see that there are 135 interval type 2 second order rule partitions. Okay, so let's compare the type 1 and the interval type 2 fuzzy systems. What we see is that the interval type 2 fuzzy system, which has the same number of first order rule partitions as, there's a typo here, it should be interval type 2 fuzzy system, has close to twice as many interval type 2 second order rule partitions. Consequently, the interval type 2 fuzzy system is able to provide a much greater and finer sculpting of the state space than is the type 1 fuzzy system. And this happens automatically. When you design your interval type 2 fuzzy system, whatever method you use, that's what's going to lead you to the FOUs to these 2 variables, X1 and X2. And automatically, as a result of that design, you have sculpted the state space using 2 tools. The first one provides the coarse sculpting. The coarse sculpting tells you how many rules fire in a particular region of the state space. The fine sculpting tells you that in each of those regions, the formula is changing, sometimes frequently. And that's providing you a much finer sculpting than using a type 1 fuzzy system. So here's another example. Here's an example that sometimes people use in fuzzy PID control. They have 2 variables, error and error rate, and they choose these diagram. And you can see that there are 4 regions And there are no second order rule partitions here. In each of these regions, the membership function doesn't change. Okay. Now let's go to the interval type 2 version of this. Now again, this is the complete construction of the first and second order rule partitions. There are 4 first order rule partitions, in each of which 4 rules fire. But now you can see that because we have a lower membership function and an upper membership function, the uncertainty associated with the membership functions provides a fine sculpting. In each of these 4 regions where 4 rules fired, there are 9 second order rule partitions. 9. So what that means is that over the whole state space, there are 36 second order rule partitions. So this interval type 2 fuzzy system has much greater variability than the type 1 fuzzy system. And it's the variability of these second order rule partitions that provides this system with the potential for outperforming its type 1 counterpart. Okay. So generalizing this in a type 1 or an interval type 2 fuzzy system, a type 1 or an interval type 2 second order rule partition of the state space occurs when the membership function, or the FOU, of the respective fuzzy set associated with any of the variables changes its mathematical formula. Okay. Geometric approach is impossible if you go from 2 to 3 variables. You can't see the regions and count the number of partitions. In my paper, whose reference I'll give you later, I have a formula that will give you the total number of second order rule partitions. In order to use that formula, you have to know how many second order rule partitions there are for each variable separately, and you also need to know how many first order rule partitions have 0 second order rule partitions. It's a little tricky, but it's not that difficult. I'm not going to go through that now. Now, we come to something truly novel for interval type 2 fuzzy systems. In addition to first order and second order rule partitions, if output processing involves type reduction, then there's another partitioning of the state space, and that partitioning is something that I call novelty rule partitions, and it only occurs when you use type reduction. And as a result of different endpoints of a firing interval being used to compute the endpoints of the type reduced set. Remember, if I talked about those switch points, I'm not going to go back to the formula. You have to determine where those switch points are, where you switch from an upper to a lower membership function in order to determine the left and the right endpoints of the type reduced set. Okay, because there's no closed form formula for the type reduced set, it's not easy to determine the geometry of these. What's important, though, is that they never occur in a type 1 fuzzy system because there is no such thing as type reduction. They may also help to explain why system performance is often arguably better for an interval type 2 fuzzy system that uses type reduction than it is for one that doesn't use type reduction. People may ask you, why do you need So now it's time for a more serious example. So let me look at a fuzzy PID controller. Here's the block diagram for it. There are two variables, error and error rate. And here's the structure of the type 1 fuzzy logic controller. If error is F1 and the error rate is F2, then the control is G. And in the example, I'm going to assume that each of the two variables has three membership functions. Remember, I showed you those, negative, 0, and positive. And through the design of this first order fuzzy logic controller, here's what the consequent is for each of these rules. It's in this table. So there are 9 rules. It's unimportant how I got those numbers. Here are the three membership functions for each of the variables. They have the same structure. And each of the outputs is a singleton. They can have linguistic names if you want, although that's not really important. This figure here correlates with this table. So for example, when U is negative big, then it's the value of -1. When U is positive medium, then it has a value of 0.5. Okay. So, I went backwards. Oh, I know, I'm sorry. Now what I'm going to do is I'm going to show you the interval type 2 counterpart. Structure of the rules is the same, except the fuzzy sets are replaced by type 2 fuzzy set. The controller is going to have the same structure. The only difference between the type 1 and the interval type 2 is that now each variable has 3 fuzzy sets, each defined by its FOU, shown in this diagram. And now what I want to do, okay, so let me explain what I'm going to do. Remember, I told you that a fuzzy system is a mapping between the input and its output. So I'm going to show you what that mapping looks like for some of these fuzzy systems. So here is the input-output surface, okay, E, delta E, and U, for the type 1 fuzzy logic controller. In terms of this example, I'm at this point here, okay? So I'm going to show you the nonlinear surface between the two inputs E and delta E and the output. And so I'm going through the 9 rules, and I'm writing down the formula, and I'm writing a program, and then I'm evaluating that output U for all values in E and delta E. You know, it sort of looks like a linear plane. Here's the surface that I get using center of steps type reduction and defuzzification. And you can see that this really looks nonlinear. It's got wiggles and jiggles. Although I didn't talk about the details of another kind of interval type 2 fuzzy logic controller, this is one due to ni and tan, that's why it's NT, that bypasses type reduction, and it goes directly to a numerical output. And the reason that I'm showing it is you can see that when you go through type reduction, it looks like you're further partitioning the state space so that you get this nonlinear curvature. And frankly, there's not a heck of a lot of difference between the surface of the ni-tan and the type 1. Okay, if I blew it up, you would see, yes, there is some curvature in the ni-tan, but not a lot of it. I mean, let's face it, the type 1 and the ni-tan diagrams look almost the same. What really looks different is the center of set diagram. So let me show you what the partitions look like for this example. Okay, I have 2 diagrams here. The left diagram shows me over the whole state space to compute the left end of the center of sets interval. So in some parts of the state space, L is equal to 1. In other parts, L is equal to 3. The diagram on the right shows you where the switch is occurring in order to get the right end of the interval. Now you may say, how did I get these figures? By brute force. I had to go to every region and I had to compute using one of these iterative algorithms, the KM or the enhanced KM. Doesn't matter what algorithm you use, you'll determine the left switch point and the right switch point. Okay. These two diagrams demonstrate that when you do type reduction, there's a further partitioning of the state space. And if I go back to these figures, you can see that the nonlinearity that you're seeing is in part due to this further partitioning of the state space. Can only occur when you use type reduction. Never occurs in a type 1, never occurs if you don't use type reduction. So this brings me to some conclusions. First conclusion is that it's the greatest sculpting of the state space that usually lets an interval type 2 fuzzy system outperform a type 1 fuzzy system, and usually lets a type 1 fuzzy system outperform a crisp system. We talk about coarse sculpting and its first order rule partitions, and fine sculpting with its second order rule partitions. It's not uncommon at all for an interval type 2 fuzzy system to have vastly more second order rule partitions than a type 1 fuzzy system, which means it has a vastly greater fine sculpting capability than a type 1 fuzzy system. Novelty partitions only occur in an interval type 2 fuzzy system that uses type reduction and provide an interval type 2 fuzzy system with an even greater sculpting capability. So what I've been able to do is talk about the potential for improved performance of any kind of fuzzy system over either a non-fuzzy or its lower kind of a fuzzy system in an application-independent way. Let me say that again, in an application-independent way. Now, we've made extensions to what I've described. Non-singleton type 1 and interval type 2 fuzzy systems. This is where you model the measurement using a fuzzy number because you believe that there's measurement noise, uncertainty about the measurement. We've extended this to general type 2 fuzzy systems. That is, how do we explain the potential for further improvement in going from an interval type 2 to a general type 2? We've also used partitions to explain why an intuitionistic fuzzy system has tremendous potential for outperforming either a type 1 or an interval type 2 fuzzy system. We invented something called patch learning. And then most recently, I've used partitions in work on explainable AI. Now, because I have some time left over, I'm going to talk about some of these extensions, the non-singleton, the general type 2, and the patch learning. So non-singleton fussification is used when the measurements that activate It models such a measurement as a fuzzy number, so that regardless of the cause of a measurement's imperfections or uncertainties, they're treated within the framework of fuzzy sets and systems. So here's what I mean by a type 1 fuzzy number. For variable x sub I, you make a measurement, xi prime, but you're uncertain about it. There's uncertainty. And so I'm going to model it not as a singleton, but as a triangular fuzzy number. Now, why use a triangle? Well, I use a triangle because the measurement is being made at x prime. X prime is x prime. There's no uncertainty about x prime and what that value is. However, you believe that there's uncertainty about that measurement, and so I'm allowing a band of uncertainty about x prime equal to 2 delta. And so now, when you model the input as a type 1 fuzzy number, the inferencing becomes more complicated. That's the price you pay. If you want to model uncertainty, you now have to go through and compute the firing level using the t-norm of this formula here. You've got to take the maximum between this membership function and the membership function of its antecedent, where this star is either a minimum or a product. I'm not going to explain how to carry out that computation, but that's what you have to do. For an interval type 2 fuzzy system, remember, instead of a firing interval, a firing number, you get a firing interval. And now the computations for the left end and the right end of the firing interval involve 2 more complicated computations. The left end with the underbar, you have to solve this soup star composition using the lower membership function for the antecedent. So now you're taking this max star between a type 1 fuzzy number for the measurement and also a type 1 fuzzy set, but it's the lower membership function for that antecedent. To get the left end or the right end of the firing interval, you use the upper value. Again, I'm not going to go through those computations. Let me show you an example for type 1 fuzzy sets of that max-min computation. So in this figure, my measurement of xi is occurring at xi prime. The membership function for its antecedent, I'm assuming in this example, is the left shoulder. So the blue curve is the left shoulder for the antecedent. I have a triangle that's centered at xi prime. And now here's the geometric construction of that max min product. The first thing I do is I take the minimum between the triangle membership function and the left shoulder. Okay, so I get this brownish looking membership function. Then it breaks down and I get the red. Okay, and now I take the maximum of that, and the maximum occurs at this elliptic point here, and that's the xi star. That's what the max min calculation is between these two. One more example. My membership function for the measurement is still a triangle centered at xi prime, and now I'm assuming that the membership function for the antecedent is given by this triangle. You first take the minimum between these two, and you get this cardinal triangle, and then you take the maximum, and it's at the intersection of these two. So geometrically, that's what's going on. And what I want, the reason I'm showing you this construction is so that you see that unlike a singleton fuzzy system where you would use xi prime because you believe that there's no uncertainty, when there's You're doing some kind of front-end filtering. You can think of non-singleton fussification as allowing you to perform some filtering of your noisy measurement. So now what I want to do is I want to construct the first order rule partitions for singleton and non-singleton, so you can see what the difference is. So this is the construction that we went through earlier for the singleton type 1 for two variables, x1 and x2. Both have three membership functions, low, moderate, and high. And now, okay, the construction of this diagram for non-singleton requires that you have gone through the mapping of the soup star composition. And when you do that, that will give you points along the x-axis that are different from the A and B and the C and D that were used in singleton. Okay, this is all explained in another journal article. But now you get different vertical and horizontal lines. And, whoops, and what you can see, by the way, this 12% means that the band, the 2 delta, was 12% uncertainty on each of the measurements. And when I compare these two diagrams, remember, this is all type 1, what I see is that a non-singleton fuzzy system also fires more rules more often and fewer rules less often. It acts sort of similar to an interval type 2, interestingly. And that's the way you handle uncertainty. It doesn't matter whether it's measurement uncertainty or membership function uncertainty. Uncertainty in a fuzzy system is always geometrically explained by there are regions where more rules fire more of the time and less rules fire less of the time. Okay, you're averaging to accommodate for uncertainty. I want to recall that this is the first order rule partition for singleton interval type 2, and we have the same conclusions. Here's the non-singleton interval type 2. Okay. And you can see that, wow, now there's even more real estate allocated to firing 4 rules than there was in the singleton interval type 2. So here are the 4 diagrams side by side. And what you can say is that as you go from a system that doesn't model any kind of uncertainty, measurement or membership function, the regions in which you fire more rules gets larger and larger as you accommodate measurement uncertainty and membership function uncertainty. I think this is very, very clear. Okay, the bottom diagram is the one where you've handled both the measurement and the membership function uncertainty. And if you were to compare that diagram with the upper left one where no uncertainty was modeled in the fuzzy system, you can see the vast shrinkage of the regions where only 1 rule is fired and the huge increase where 4 rules are fired. Now, again, I want to remind you, this is a 2-variable system that has 9 rules. It never fires even 5 rules. The most it fires are 4 rules. But this is the way uncertainty is accommodated for in a rule-based fuzzy system. Non-singleton fussification acts as a front-end filter, spreading out the regions where more rules are fired. And interval type 2 also spreads out the regions where more rules are fired and fewer rules are of the coarse sculpting of the state space accomplished by pre-filtering and the max-min or the max product composition that provides a non-singleton type 1 or interval type 2 fuzzy system with the potential to outperform a singleton type 1 or interval type 2 fuzzy system when measurements are uncertain. Now you'll notice I use the word potential because now in order to demonstrate the actual performance improvement, you have to go to your particular application and examine its widely accepted performance metrics. If, for example, you were looking at a forecasting problem, you would look at the root mean squared error. If you were looking at a classification problem, you would look at the misclassification rate. If you were looking at a control problem, you would use control metrics like rise time, percent overshoot, the integral of the absolute error or the time absolute error. Okay, and you would have to compare those against a non-fuzzy system, a type 1 fuzzy system, an interval type 2 fuzzy system. But sculpting the state space gives you a great hope and feeling that the fuzzy system will indeed outperform the non-fuzzy system, finally explainable in terms of the application's metrics. So now let me talk about another application, something that we call patch learning. So I want to remind you, in machine learning, there's different strategies that people use to enhance the performance of an underperforming machine learning model. You could use a single deeper model, meaning more layers. You could use a single broader model, meaning more inputs. You could use a more nonlinear model, that is, you make the neurons more nonlinear. You could connect multiple simple models in parallel, or you could connect multiple simple models in series. There's no end to it. So we invented something called patch learning that connects multiple simple models, both in parallel and in series, to improve the learning performance. And here's what you do. You train an initial global model using all the training data. This could be type 1, it could be type 2. Then what you do is you identify L patches in your state space from the initial global model, which contribute the most to the learning error. Then you zoom in and you train a local patch model for each such patch. So what's a patch? Well, a patch is a first order rule partition. And we have formulas for labeling the patches using a single index and for mapping an input vector into its patch. Then what you can do is you can update the global model using training data that don't fall into any patch. So the analogy that I like to make is, let's get back to the sculptor, you're Michelangelo. And you started with your block of granite. And you've carved your figure. Within each block is a David, a figure. Okay. Now, though, you examine. So you've used a coarse tool. Now, though, you look at the hand and you say, aha, I need to refine that. And so you use a different tool, a finer tool, and you resculpt that hand so it looks more and more beautiful. However, a hand has to be connected to the arm. Okay, so you've zoomed in on what might be that first order patch, that hand, and you've modified it. But now you have to blend that hand in to the rest of the figure. And then you can do that for the arm and the shoulder and so on and so forth. That's the idea of patch learning. You zoom into a region where you have the greatest errors. You do better in that region, but then you have to once the patch learning models are trained, you come in with a new input and you ask, does that input belong to a patch? If the answer is no, remember, a patch is where you've made a change. Then you use the global model to compute the output. If their answer is yes, then you use the patch model to compute the output. It's as simple as that. So the journal article, and I'll give you the reference, in that journal article, we applied the patch learning concept to these 5 problems. And in all the problems, we demonstrate that patch learning outperformed either no patch learning or bagging and boosting. Patch learning was only possible because we had developed the concept of first order partitions, because it's those partitions that let me zoom in to well-defined regions of my state space where the largest errors are occurring. To date, only fuzzy systems let patches be defined. I don't think you can do this using neural networks. And the reason that's so is because although neural networks are fabulous and they provide a nonlinear formula also between the input and the output, from a geometric perspective, they begin at a high level. A high level means you think about doing things to all of the variables all of the time. So for example, if you use radial basis functions, you think about those basis functions in terms of the whole state space. You don't think about partitioning it. So it's more of a top-down approach to nonlinear processing. Fuzzy systems is more of a bottom-up. You begin by first examining each variable, creating membership functions for them, and then combining all of that to get the global partitioning. And now we understand that because we can partition each variable using first order partitions, okay, that automatically partitions the whole state space, okay? So now let me talk about general type 2 fuzzy systems. Okay, so in the beginning, there were only fuzzy systems that later had to be called type 1 fuzzy systems when people started working on type 2 fuzzy systems. And then, because general type 2 fuzzy sets and systems seemed so complicated, people focused on interval type 2. And then a marvelous decomposition occurred that let me mathematically represent a general type 2 fuzzy set as a collection of planes, horizontal slices. Each of those planes can be described using interval type 2. So a general type 2 can now be thought of as a collection of interval type 2. And this is a diagram that gives you a high level description. The combining of what's going on only occurs in the defuzzifier. For general type 2 fuzzy systems, you have to also describe the secondary membership function. So here is the footprint of uncertainty for a variable x. And now, unlike an interval membership function, where the secondary grade is always unity, here I'm assuming the secondary grade is a triangle. And I think you learned about alpha cuts. Each of these triangles has an alpha cut, and you can imagine connecting all these alpha cuts for all of the triangle secondary membership functions and getting a plane. that the numbers of first and second order rule partitions are exactly the same for interval and general type 2 fuzzy systems. This is explained in yet another journal article. You just have to believe that. This general type 2 fuzzy system that I attribute to Christian Wagner and Hani Hagris, and I like to therefore call it a WH, general type 2 fuzzy system. Remember, it's this interconnection of interval type 2, okay, always has the maximum number of changes in each of its second order rule partitions for each of its horizontal slice fuzzy system, whereas an interval type 2 fuzzy system doesn't. Okay, so what it means is, I know this is hard to really follow, but let me try. Imagine the second order rule partition diagram for an interval type 2 fuzzy system. What I haven't told you is in each of those second order rule partition, what's causing the change? Is it a change in the upper membership function, a change in the lower membership function, or both? It turns out in an interval type 2 fuzzy systems, sometimes it's one or the other of those. It may be a change in the upper, it may be a change in the lower, or it may be a change in both. In a WH general type 2 fuzzy system, what I'm able to show is that in each of the second order rule partitions, it's always a change in both. It's always a change in both the upper and the lower on each of those horizontal slice. That's the additional variability due to going from an interval type 2 to a general type 2. When type reduction is used in a general type 2 fuzzy system, it's done on each of those planes. And so the total number of novelty partitions is directly proportional to the number of horizontal slices. Consequently, there are many more novelty partitions in a general type 2 fuzzy system that uses type reduction than occur in an interval type 2 fuzzy system that also uses type reduction. Here's my conjecture. It's the maximum changes that occur in every second order rule partition, as well as the greater number of novelty partitions when type reduction is used, that provides a general type 2 fuzzy system with the potential to outperform an interval type 2 fuzzy system. Now my overall conclusions. Sculpting the state space in terms of first order rule partitions, the coarse sculpting, second order rule partitions, the fine sculpting, and novelty partitions, only available when type reduction is used, leads to new explanations for why performance improvements may be possible for type 1 fuzzy systems over non-fuzzy systems, interval type 2 over type 1 fuzzy systems, general type 2 over interval type 2, and non-singleton over singleton fuzzification. These explanations are geometrical, they're easy to understand, and hopefully you can use them to convince others of the value for using different kinds of fuzzy systems. Partition theory has also led to new results. Okay, in one of the papers on non-singleton fussification, you're going to see that there's a new phenomena that I call rule crossover, in which combination of rules fire that can never occur for singleton fussification. And I can now explain that. No one ever realized this before using partitions. Patch learning, a new kind of machine learning, can only be implemented using fuzzy systems where the patches are the regular fuzzy systems because, as you'll see in the journal article, they have vastly more first-order rule partitions than the latter. We're able to explain one of the unique features of adaptive variable structure basis function expansion, the coarse and fine sculpting of the state space using partition theory. Explainable AI, partition theory lets us locate the rules that have contributed the most to an output. And you're going to find that it's a very small subset of the total number of rules. Finally, here are the references if you want to dig deeper. The first paper is an explanation that compares type 1 and interval type 2. The second paper ups the ante, compares interval and general type 2. The third paper compares singleton and non-singleton, both type 1 and interval type 2. The fourth paper is about patch learning. The fifth paper talks about intuitionistic fuzzy systems. The sixth paper explains what I call adaptive variable structure basis function expansions. The history of that is as follows. You may know that in 2017, I came out with the second edition of my textbook. And what I realized is that you have to invest a lot of time to learn about fuzzy systems before you can even write the formula for the simplest, a type 1. Today, people want to be able to use a nonlinear system in machine learning without having to invest a lot of time. The beauty of neural networks is you really don't have to know much before you get to that formula, y equals f of x. The downside of fuzzy systems is you have to know a lot in order to understand how you get that formula. So in this information sciences paper, I take a different approach. I say, well, okay, what a user is really interested in is the product, the formula, y is equal to f of x. What are the products and what are their properties? I'm not interested in how I get the product. I'm interested in, tell me what the products are, tell me why I should use them versus other products. What can they do that can't be done? And what you'll find in that paper is that the answer to those questions uses first and second order rule partitions. And so using what's in that paper, you don't need to know anything about fuzzy sets. Nothing. And finally, a very, very recent paper just came out this month in TFS is a paper that's called Critical Thinking About Explainable AI for Rule-Based Fuzzy Systems. There's this feeling that because rules use words, fuzzy systems are explainable. I hate to disagree with that, but you'll find in that paper how we can explain what's going on and how we should explain what's going on for the most popular kinds of rule-based fuzzy systems. And partition theory helps me to do that. Without partition theory, I couldn't do it. So, whoops. I guess that brings me to the end of my presentation. And so I'm going to stop sharing now and turn it back to you. I guess this might be a time, if there were questions, I'd be glad to answer questions. Anupam?
Yes, sir. So if anyone has any questions, they can ask. So we have one question in chat box. Shall I read, sir?
Yeah, I can read it. How to decide when to use type 1 or interval type 2 fuzzy sets on the output side in the interval type 2 fuzzy PID controller. Is it possible to get any hint from the plant or sensor dynamics? Well, I'm a great believer in achieving just enough performance so that you've satisfied the performance specifications. Okay, so if you're working in process control and you want to design a fuzzy PID process controller, there have to be some performance specs that you're shooting for. Okay, if you're able to meet those performance specs using a type 1 fuzzy system, why go on? Okay, if you can't, then I would go to the next level. I would use an interval type 2. And again, see, can I meet the performance specs? Now, meeting those performance specs is subject to how much uncertainty is there. If you believe that there's no uncertainty about the measurements, that's a much easier design problem. If you believe there's uncertainty about the measurements, then that's more challenging. So I'm not a great believer anymore of optimizing the heck out of the system to get the ultimate or the penultimate performance. If you work for a company, your job is to design a product and sell that product to someone else. Maybe it's within your own company, or maybe you have a product and you're marketing to somebody else. So you sell that product. And then in time, the performance requirements get even more stringent. Okay, now you have to come up with a better product. Imagine, for example, if Apple Computer wanted to come up with a penultimate phone or computer, we still wouldn't have a product. What they do is they entice us with devices that meet certain performance requirements, and we buy those things. Then they gradually entice us with more performance, and we update, and finally we got to upgrade or maybe buy a new device. They're in business to make money. Okay, they're not in business to come up with a penultimate iPhone or computer. I'm sure that they have looked years into the future and they have a plan for coming up with this update, this upgrade, and so on and so forth. And what do? We spend more money to buy those things. This is a roundabout answer to this question that you have performance specs when you work in industry and you try to achieve those. When you achieve those, stop. As they get better, redesign, come up with a different product. I hope that's the answer to the question. So I have another question. Could you give some more web links for interval type 2? I have a private web link. God, I'm trying to remember it. That has a huge amount of resources. I mean, huge. Hang on 1 second. Let me, whoops. Are you still there? Yeah, okay. Let me, hopefully this works. I'm going to try and open this. Okay. Give me a second. Okay, so I found it. If you go to jmmprof.com, that will open up to a very, very extensive website. As I mentioned, it has a huge amount of resources. It also has direct links to what I call my Sculpting the State Space series. It has extensive Type 2 references, software sources, and supplemental materials for a recent IEEE Computational Intelligence magazine article, and also more material that supplements my 2017 book. So I hope that answers the question. There's a lot of stuff out there. Oh, good. Someone's put the link on there. Yeah, I would start with that. That'll keep you busy for a long time. Any other questions? Well, I hope you've had a very worthwhile course, and will now try out some of these fuzzy systems. What do you think, Anupam?
Sir, I have one question. What is future of fuzzy in machine and deep learning in coming years?
Say that again. I didn't hear you. Say that again.
So what is future of fuzzy, especially type 2 in deep learning and machine learning? Because everyone is behind the deep and machine learning.
Well, fields tend to move where the funding is and where the action is. And today, machine learning is ultra hot. And that was one of the reasons that I wrote my adaptive variable structure basis function expansion paper, is because what we're doing can be sold in different ways. And that paper tries to sell the products as a store full of very interesting and powerful basis function expansions. And what I'm hoping is that people will try those, because they're just a different nonlinear mapping between inputs and outputs. And machine learning methods can be used to optimize the membership function parameters. Now, what I must tell you is that I'm working on another project with Hani Hagras, and we're putting together a journal article on what I think is something that's extremely important and has not been paid attention to, surprisingly, for the most part, in the whole history of fuzzy systems. Now you may say, what? How can this be? So let me tell you what it is. When machine learning techniques are used to optimize a fuzzy system, what you're trying to do is you're trying to optimize the parameters of membership functions, or FOUs. I'll just use the word membership function for any kind of fuzzy system. But that's a constrained optimization problem. Constrained? What do you mean constrained? It's constrained because membership functions have constraints associated with them. If, for example, your membership functions are triangles, then the three coordinates have a relative relationship to one another. In addition, you want the membership functions to overlap. That's a geometric constraint. You can't have a gap between membership functions. That's very bad. Constrain the membership functions ahead of time so that they preserve the shape and they preserve overlap. When you constrain membership functions, you reduce the degrees of freedom. when you reduce the degrees of freedom, you reduce the potential for getting best possible performance out of your system. So what we have to recognize is that optimizing a fuzzy system is a constrained optimization problem. Now, what I did is I came up with a transformation of parameters that can be used during the tuning of these systems so that all constraints are satisfied. You never have to check them. Never. They're automatically satisfied. So what happens is during the tuning, instead of optimizing the original parameters, you optimize a related set of parameters. So for example, suppose you're using any kind of machine learning technique. I don't care whether it's BP, whether it's GA, whether it's some other particle-based method. Every time you change something or you update the membership function parameters, you have to check to see whether you've preserved the integrity of the constraints on the membership functions. That takes a lot of time, a huge amount of time. If you don't do this, you could wind up with nonsense. You could wind up with a triangle that all of a sudden changes shape, and this is no longer a mathematical function. It's only a function if it looks like that. If it looks like that, it's not a function. So using these new parameters, and for example, if you're using GA, okay, where you have to generate many chromosomes, and you have to perform all these tests to make sure you preserve the integrity. By the way, you may be wondering, how many tests? Well, for interval type 2, it's a lot of tests. You have to test the overlapping of the upper membership function, lower membership function. You have to preserve the integrity that the lower membership function has to always be within the upper membership function. Okay? That's why people don't do this. They constrain, and when you constrain, you lose performance. Okay? Using the parameter transformations, what I've proven is that you do not reduce the number of degrees of freedom. When you pre-constrain, you always reduce the number of degrees of freedom. Using these new parameters, you have the same number of degrees of freedom. And so we're now running simulations and we're showing vast improvements in performance and in computation time. Why this is important, sorry for this long-winded answer, is because we believe that fuzzy systems can be very valuable in machine learning. But the machine learning people are going to be stymied by the constraints. They don't like constraints. It takes too long. If you use neural networks, there's no constraints. You just optimize. So now I've sort of leveled the playing field. By using these new parameters, there's no constraints either. Okay. Anyway, so I have another question. How can we implement fuzzy logic type 2 in motor control? I can only refer you to people who do type 2 fuzzy control. Let me give you some names. There's a Professor Hao Ying, Y-I-N-G, who's at Wayne State. He's published on fuzzy logic control. There's Tufan Kumbasar. He's a Turkish associate professor now. He's published a lot. Your question. Another question, is there any relation between type 2 fuzzy sets and interval value fuzzy sets? Please explain. Oh, I love that question. I love that question. One has to go back to the history of fuzzy sets. I wrote a parody that appears in the Computational Intelligence magazine, where I trace the history. And eventually we get to Professor Zadi's magnum opus, his 1975 three-part information sciences paper, where, for whatever reasons, which he never explains, he introduces two generalizations of type 1. Anupam, are you there? Am I still online? Hello?
Sir, you are online, sir.
Yes, sir. Yes.
Oh, okay. Okay, so let me explain what they are. The first one he called interval valued fuzzy sets. He had a slightly different name. And the second one was a fuzzy set of type 2. Later we call that type 2 fuzzy set. So it was in that paper that he introduced these two kinds of generalizations. And historically, some people looked at general type 2. The computer power didn't exist in the 1970s, and nobody really knew what to do with them. How do you perform the classical operations and so on and so forth? Much more attention was paid to interval valued fuzzy sets, and there's a rich literature on that. And I would say the champion, if you had to say a champion for those, is Professor Humberto Bustins, who's in Spain. When we got into type 2 fuzzy systems, we began with general type 2 fuzzy systems. If you go to our first paper, you'll see that it doesn't specialize to interval type 2. And that turned out to be a really good thing, because we had to invent type reduction. Okay, and type reduction makes very heavy use of the nature of the secondary membership functions. Then, when we later specialized this to interval type 2 fuzzy systems, we still used type reduction. Okay, and so there was a natural progression from general, where there's a full-blown secondary membership function, to interval. But you know, an interval type 2 fuzzy set also has a secondary membership function. It happens to be unity. Now let's go to interval value fuzzy sets. Interval value fuzzy sets have no secondary membership function. They live on the FOU, none whatsoever. Okay. Now, the interval valued fuzzy set community likes to claim that their sets are the same as interval type 2 fuzzy sets, and that there's a great similarity between a little bit of what they did and what we did in interval type 2 fuzzy logic systems. I was initially swayed by that, but when I finally wrote my second edition, I have a big footnote about why I no longer believe that they're the same, and I make an analogy. So let me make the analogy. Suppose you have a skyscraper, okay, a building. Interval valued fuzzy sets represent the foundation, the bottom layer. Interval type 2 fuzzy sets not only represent the foundation, but they represent the whole rectangular building. Because membership function, and therefore there is a difference between these two. Okay? So when we began with general type 2, Bob, John, and I sequestered ourselves one time. I visited him at his university, and I had the idea, you know, there must be a way to explain an interval using type 1 or simpler. And so we came up with this representation theorem that a general type 2 could be represented as the union of simpler type 2. They're like foils that, if you take the union of them, represent the general type 2 that includes the secondary member. Remember, general type 2 is a three-dimensional object. I mean, it's hard to visualize this. The same thing is true for an interval. That is, an interval type 2 or an interval valued fuzzy set on its footprint can be represented as the union of all the type 1 fuzzy sets that are embedded in it. Those notions never were developed by the interval valued fuzzy set community. They always thought just in terms of the boundaries, the upper and the lower bounds. So I believe that conceptually, yes, there is a difference. There may be some relations. Those are all explained in my book now, what the relations are. We've had a very, very healthy and important dialogue between the interval type 2 and the interval valued communities. Anyway, so that's the long-winded answer. Wait, I have another question. Can you please suggest some reference books to understand type 2 fuzzy sets and type 2 interval fuzzy sets geometrically? Yeah, go to my 2017 book. It's all there. Everything you want to know is there. And it'll guide you. If you're only interested in interval, you don't need all the stuff about general type 2. But if you want to go farther, it's all there. That's the book that I would suggest. Any more? I don't see any more questions. So
I hope you have answered all the questions.
okay, well, I've enjoyed this presentation, and I hope all of you have found it informative. It takes some effort to get into the type 2 field, but I believe it's really worth it because of the potential for improved performance. But what I would do, getting back to, okay, where is this field going, is I would describe what you're doing in terms of machine learning language now, because that's what the world is into. They're not really into fuzzy stuff. Okay.
Yes, sir.
So is that it? Can we end?
So, yes, sir. Thank you, sir, for your informative and great knowledge about type 2. And this is first, I can say that this is first session kind of, I got a lot of information related to type 2 because very less amount of data is available on YouTube or other places, like a video form. So thank you, sir. Thank you very much for this informative session.
Okay. So I'm saying goodbye and good night, although I'm first starting my day. Okay. So long.
Thank you very much, sir. तेज जी, please stop the recording.
Yes, sir. अभी कर देता हूँ.
Right. So thank you everyone.